talk about linear time samplers for supervised topic models using compositional proposals. I'm Xing. So there are three keywords you need to pay attention. First is linear time. It's linear time in topics and supervised topic models, although we're in the unsupervised session. And compositional proposals means using some flexible ways. I'm sorry, just change to. Okay, much better. So compositional proposals means we use we take advantage of some versatility in MCMC methods. So before we talk about supervised topic models, let's first focus on the wider problem, which is mixture models. Oftentimes we encounter this problem, which is collapse scheme sampler for mixture models, and the bottleneck of this algorithm is in the sampling part. We need to sample from a discrete distribution or the multinomial vector, and this is the most time-consuming part. If we break down this into two pieces, first we need to compute the discrete distribution pi, and then we simulate from that pi. So this, if you think about it, it really lies in the basis of every stochastic simulation method. So we need to think hard about this. So 99% of people who use this method basically compute the normalizer and then sample from the distribution. The method consumes OK time. And there is a slightly improved version called inverse probability transform. It's a classic method in statistical inference. It basically replaces the simulation with binary search on the CDF of probability vector, since CDF of discrete distribution is naturally sorted. And then here comes a sort of mind-blowing method. So if we have for example, if we have a probability vector 0.6, 0.2, 0.2, we can simulate 5 state vectors consist of three states, three A states and one B state and one C state, and we randomly draw one of them. And that's also a valid sample, and this costs O1 time. I wrote a question mark there because the construction of this table depends on many factors. For example, if pi has a huge number of precision, we can actually emulate. You can actually simulate it precisely, right? And here comes yet another method. It's called Alias Method. It's kind of a ultimate weapon in this field. In this sampling from discrete distributions. It's also a key core idea of last year's best paper. It's basically builds an alias table first and then draw from alias table with a one time. So this figure is a one-figure summary of alias method. Basically, if we have a probability vector, we rob some probability mass from the rich guys and send it to the poor guys, and we form a rectangular area here, and each bar only consists of 1 or 2 states. So when we draw from this, we just randomly throw a dart on the rectangle. Because it's a rectangle 2D, we need 2 uniform random variables, and it's O1, of course. But there's one more step when we apply alias method to collapse scheme sampling in mixture models. That is the distribution, conditional distribution is changing when we sample the one assignment, right? So we can't afford rebuilding it over and over again because it takes OK linear time. So we need to correct the idea is to build the alias table once and then reuse it multiple times and correct from the delayed statistics. And here it's a familiar metropolis Hastings correction. So we just draw from the distribution and then correct with some acceptance probability. So in summary, the kind of ultimate weapon in collapse sampling for mixture model is that it's metropolis within Gibbs with using alias method in drawing samples. If we update the alias table infrequently, we can achieve the amortized O1 time complexity. So this is also the core idea of this paper. And we apply this trick to supervised topic models. So before that, let's first quick review of supervised solving models. So I'm sure everybody is kind of familiar with this posterior inference for LDA. So we want to find the posterior in this form or the collapsed form of this. There's an interesting perspective of Bayes' theorem from an optimization point of view. If we instead of seeking for P posterior, we can ask another problem, which is ask another question, which is find the Q such that it's closest to P. If we replace the KL divergence with the Euclidean distance, then the meaning is quite simple to get. We're asking if here's a point P, and what is the closest point to it? It's itself, right? It's actually saying nothing. But this optimization point of view of Bayes' theorem gives some flexibility in modeling. Just a side note, the familiar variational inference can be viewed as the same optimization problem constrained to some set. So it's kind of a projection operator. So if we have some metadata such as labels in the documents, we can add a convex loss to the original L. L is the objective function here. And we end up with a richer model that can incorporate metadata quite nicely. Because the KL divergence is strictly convex in Q, so we have a unique solution. And then if we add a convex loss to that strict convex objective, we end up with another strictly convex problem. So the solution of this problem is also a unique solution. For example, we can add a hinge loss, expected hinge loss, but since everything, eta, the classifier eta and the topic assignment z are random variables, we need to take expectation of it. So how do we end up, we have a model now, we have a formulation, how do we perform posterior inference? In fact, it has a closed form solution. It's quite easy. It's only the only different part from the vanilla LDA is the red phi here, which is nothing but exponential over hinge loss. But we have a max there. It's quite nasty. It's not usually seen in statistical inference, and it's hard to derive conditionals or so the best we have is just do variational inference. But in this work, we want to use Gibbs sampling. You'll see how we transform this into a nice conditionals. So we need a crazy looking theorem like this, but it's saying nothing but exponential over some function can be written as an integral of normal density. So things inside the integral can be seen as a normal density. So how do we make use of it? So originally we have this nasty part in our posterior. The max is the hard part. And we augment with an auxiliary variable. We actually increase the problem dimensionality, and we end up with you'll see we end up with easier to solve problem. So we've transformed the hard part into something looks like inverse Gaussian or normal density. And after collapsing, which is a standard procedure in collapsed Gibbs sampler, we end up with the final posterior to work with. The blue P there is the usual LDA collapsed posterior, and red phi here is the richer metadata information. So if we derive the conditionals, we can find that both the auxiliary variable and the classifier, the metadata, has very nice conditional and analytical forms of conditionals. So the auxiliary variable follows the inverse Gaussian distribution, and then the topic assignments follow, as in LDA, follow the discrete distribution and with some extra term, and eta follows multivariate Gaussian. But let's look at the complexity. Inverse Gaussian can be sampled in constant time, so it's easy. But discrete distribution, previously, it takes linear time, so it's quite inefficient. And multivariate normal density, we have outer product there. So it takes square k time, And then to sample from a multivariate normal, we need to factorize the covariance or precision. So we need to do Cholesky decomposition, and it costs cubic time. So it's quite crazy. So in total, some crazy complexity. So how do you accelerate Z part? Recall that the conditional looks like something like 3 terms multiplied together. And we can come up with easy proposals, like the first term as a proposal and second term and third term. And each of the proposals is actually a valid proposal in metropolis testing because we are as long as we evaluate with correct distribution, we are in good shape. But only working with one of them will cause some slow convergence. So we need to bring in as much information as we can. So we need to kind of combine these proposals. So here's the theorem by Tyranny, and this says we can combine different MCMC kernels with different methods, with different approaches. First is cyclic. So K1 multiplied K2 corresponds to sampling from K1 and K2 cyclically. And then the convex combination of K1 and K2 means we sample from K1 with probability lambda and sample from K2 with probability 1 minus lambda. And extension to more than 2 kernels should be straightforward. So we use exactly this method to combine our proposals. And for each proposal, we use some methods I mentioned earlier. So for PD, we use table lookup methods, and for the other two, we use Alias method. So we can achieve amortized O1 complexity. For more details, please refer to the paper. And so we end up with a much faster algorithm for Z. But is it good enough? No. I thought it was enough in the first, when I was preparing for the paper, but soon I found the sampling classifier became the next bottleneck because the complexity is cubic or quadratic in K. So we need to bring this down. The idea is noticing the Gaussian identity. So conditionals of multivariate Gaussian is also Gaussian. Then instead of sampling from a multivariate Gaussian, we just sample from univariate Gaussians. And if we compute this, we can find both the mean and precision can be computed and updated in reduced time, only linear in K. And so we completely bypass the need of forming the precision matrix, which costs OK square time. And we don't need to do Cholesky decomposition anymore. So the final complexity has become linear in K. And I need to emphasize when we use asymptotic notations, we ignore the constants. But the dominating part lies in the dn, not in the dk. So you'll see in the figure later in the experiment results, the actual complexity actually looks like a constant complexity, not linear in K. And this method also extends to other losses. I've only mentioned the expected hinge loss, but you can replace the hinge loss with other losses like regression or logistic loss. And using the scale mixture representation, we can also derive similar algorithms and apply the similar trick. So here's the experiment, binary classification. The first figure says the accuracy, and the x-axis of both figures is number of topics. You can see from the second figure shows the time. It's actually quite constant over different topics. And the accuracy, we don't sacrifice much. Here is the multi-class classification. We replace the binary hinge loss with multi-class hinge loss, and actually multitask hinge loss. And you can see the accuracy is also similar to the original slow but accurate Gibbs sampling, and the time reduced a lot. And for experiments, the last experiment we did is the different composition of proposals. So you can see the mixture of proposals, or the cyclic cycle composition of proposals, or only using one of the proposals. You can see using one of the proposals is actually a bad idea because the accuracy decreases drastically, but mixture approach still maintains the similar accuracy, but they all cost similar time. So we, in our other experiments, we all use the mixture approach. Okay, faster than I thought. Thank you.
Any questions? Go ahead.
So in your method, you in a posterior inference, you introduce some regression.
Once you start the question.
Yeah. So in your posterior inference phase, you introduce some regression term. So I have a question about. So is it possible to interpret as a compared to the exact Bayesian inference, because original variational Bayes inference can be seen as an optimization of the lower bound of the marginal log likelihood. So yeah.
Oh, let me roll back to this. So the variational inference has is slightly different from what I said here, because what I'm talking about here is here's some family. So variational inference is just this problem constrained to some family. The family is this factorizable family of distributions, right? But in this original problem, we're not talking about any constraints. We're talking about P. The calligraphic P is family of all distributions, and we just add the loss to that. So variational inference is different from the formulation part. So inference is after formulation, right? So to solve this problem, we can do Gibbs sampling or to do variational inference. And if we do variational inference, then the calligraphic P is replaced with the factorizable distributions. So and then that has become the lower bound of the marginal log likelihood.
Thank you very much.
Any last questions? Let's thank our speaker again.
Thank you.